Good morning, everyone. I hope you're all doing well. Just a few reminders. Please fill the feedback form. It's linked on end. What else? We have our midterm on Thursday. I decided to give you all the time. I'll give you all the lecture time on Thursday. We'll have the midterm for that. So it's going to be like an hour, 45 minutes. 3 problems covering kind of most of the topics we've covered between sets 1 and 10. You do not need a calculator, so don't bring a calculator, and no electronics, no nothing, just pen and I'll give you paper. Okay? If you have any questions about the midterm or any review questions, please use Ed. I also have office hours today from 1:30 to 2:30. And then on Tuesday, again, reminder, we do not have in-person class. I will post video lectures for you to watch instead of in-person class on Tuesday. And then I'll see you again on Thursday, next Thursday, after that, okay? I'm going to a conference in France, so wish me luck. Okay, so let's start today. We're covering power, work, and energy, and this topic is not included in Thursday's quiz. Okay, so we're gonna start with a few definitions. We're gonna define the mechanical power of a force F acting on a particle with velocity v as the power being F dot v. The force started with the velocity. And that's just a definition. Okay? And then we define the work done by a force F over a time interval on the particle moving with the velocity v as the integral of the power. So the integral from t1 to t2 of F dot v dt. Now, can anyone remind us what another form for v dt is? What's equal to v times dt? Acceleration. No, not quite. Position. Yes. So, right, v is dr by dt. So v dt is equal to what? Dr, right? So I can write this integral instead of an integral of as a function of time. I can write it as an integral as a function of position. So the integral from the position vector of the particle at time t1 to the position vector of the particle at time t2 of f dot dr. Okay? So the work of a force is the integral of f dot v dt, the integral of the power with respect to time. But I can also write it as an integral with respect to dr. That's the force dotted with the displacement. Force dot with displacement. And here dr is the differential displacement. Usually, yes.
You wrote power as a vector. Is that true, or is it supposed to be a scalar quantity?
Well, what do you think? Is v dot dt, is that a vector or a scalar?
That's going to be a vector, but it's dotted with f, so that makes it a scalar.
Okay, so f dot v is a scalar. So the work of a force, is that a scalar or a vector? The work of a force, the work and the power, are those scalars or vectors? Scalars, right? They're scalars that are dot products of 2 vectors. So yeah, that's a scalar, not a vector. So that's a vector and that's a vector. This is supposed to be a vector. dr is a vector then. So the velocity is the derivative of the position vector with respect to time, vector. Great. Yeah, that was a quick question. Okay. So a lot of times you hear that the work of a force is the force started with the displacement. That's only true if the force is constant. But if the force is not constant, then it's the integral of f dot that was the differential displacement. Okay? So aside, if f is constant, then the integral of f dot dr, I can take f outside the integral and get f dotted with the integral of dr, and that's f dotted with r2 minus r1. So the work of a force is the force dotted with the displacement if the force is constant. But in general, it's the integral of f dotted with dr, the differential displacement. Does that make sense, kind of? Okay. Now, what is this dr? We know from Cartesians that r is equal to xex plus yey plus zez. Let me see if you remember your calculus right. Dr. What is dr? How can I express it in terms of the Cartesian coordinates? Ideas? Yes. Exactly. And why didn't you consider the differentials of ex, ey, and ez? They're constant, exactly. Okay? Which is not the case if we're considering the position vector in cylindrical coordinates. For example, r is equal to RER plus ZEZ. In cylindricals, how can I write the R? In this case. And remember, you always have a trick to double check your answer for dr. If you do not know how to take the differential, then maybe you'll just take v and multiply it with dt and you'll get dr. So take a minute, think about it. What will dr be in the cylindrical coordinate system? Yes? What is it? dr plus dz. Close, but not quite. You have a missing term because for the this coordinate system for the polars, er is not fixed, so you have to take its differential also, right? So this is a function, a changing function. This is changing, and that's changing. So to take the derivative of this, you're going to have to use the product rule. You're going to use r der. And what is der? Exactly. Theta e theta. Okay. So far in cylindricals, I have dr is equal to dr er plus r theta e theta plus dz easy. And I can double check what's v dt. How is v expressed in the cylindrical coordinate system? The v meaning the velocity. Well, the position vector in polars is this. What's the velocity in polars? Anyone remembers? If you don't, then I'm going to have to ask you to derive it
R dot
quickly.
ER.
Yeah, r dot er plus r theta dot e theta. Right, you should be able to derive this. Okay, and if I multiply this by dt, dr r dot is dr by dt. So if I multiply that with dt, I'll get just dr. And I should get the same answer. These two should be equal, right? So then in the Serif-Frenet basis, I have dr is v dt again. And how did we express the velocity in the Serif-Frenet basis? Anyone? Yes? What was it? VET, right? VET and then dt. That would be, well, V is just ds by dt. So that would be ds et. Okay? So again, we defined what the power of a force is. The power of a force acting on a particle with velocity v is F dot v. The work is the integral of the power dt. I can write this integral with respect to time as an integral with respect to position. That's because v dt is equal to dr. And dr, I can express that using calculus in all the coordinate systems that we've learned, and in other coordinate systems even. In Cartesians, in polars, in the Serif-Renyi basis. So dr, I can get that from calculus. I can also verify that it's equal to v dt. Does that make sense? Any questions so far? Okay. So that's how we find the work of a force. Okay, let's see a few questions. When is the work of a force negative? Or when is the work of a force 0? The work of the force F between time interval 1 to 2, when is it equal to 0? Or under what condition is a force workless? Yes?
When it ends up at the same place.
So let us think about it. That's actually a little bit clever. Let us see. So if R of T1 is equal to R of T2. So let us see. The work of the force from 1 to 2 is equal to the integral between T1 or R of T1, R of T2 of F dot dr. But if these two are equal, then we're integrating over an interval that's non-existent, so basically integrating from 1 to 1. So yes, in that case, the work of the force would be 0. If the force or if the particle came back to the same location, then the integral of the force is 0. That's kind of funny. If you went on a trip and you came back to the same location and didn't do any work. Okay, what else? Under what other conditions will the work of a force be 0? Or in other words, the force be workless? When the force is, what does that mean?
So the force you put in equals the force you put out.
Not quite. We'll talk about conservative forces in a bit, but not quite. So look at the definition of the force F dot v dt. It's a dot product. So in which case is this dot product 0? Yes. Exactly. If F dot v is equal to 0, or equivalently F dot dr is equal to 0. So the force is always perpendicular to the velocity or perpendicular to the displacement. Any other conditions? I think if F is 0 or V is 0, if there's no force, then the force is workless. That's trivial. If the particle does not move, then also the force is workless. So if I have a huge box or a huge desk, and I'm pushing it, and the desk is not moving, no matter how hard I've pushed, if I haven't moved the desk, then I've not done any work. Does that make sense? In that case, V is 0. There's no displacement. Okay? Okay, I think that's the main, that's probably it. Okay, so let us think of the work. Let us consider two trajectories. Consider a particle a particle of mass m sliding down a smooth rail. And let's consider two options for the rail, straight rail and curved rail. Okay. Okay, so let's consider a particle that's sliding down a smooth rail. We're going to consider two rails. A is vertical or straight, and B is curved. We want to find the work of all the forces acting on the particle. Find the work of all the forces acting on the particle. Okay. So first, to find the work of all the forces acting on the particle, we need to find all the forces acting on the particle. So what are the forces acting on the particle in both cases? So we have some particles sliding down the rail. If I want to draw the free body diagram of the particle, how many forces are acting on it? Is it just one? What is that one force? Gravity. Weight. Weight due to gravity. So I have the weight force. Any other forces? Yes.
The normal force of the rail.
Exactly, the normal force from the rail. Okay. So if I consider a Cartesian basis, Cartesian basis, that's weight is equal to minus mg ey. Now the normal force is probably easiest to express in the which basis? I have a particle moving in a predefined trajectory that's kind of random. The Sarafinite basis. So the normal force would be along which direction? Et? En, right? En. It would have also an EB component if we were kind of in a 3D out of plane problem. But right now for this 2D problem, everything is in the plane. The normal force is along En. Okay? So let us find the work of the normal force. The work of the normal force from 1 to 2 in case A, say, or B, we will see. Is it going to be the same, or are we going to need to differentiate? The work of the normal force from 1 to 2 is the integral of n dot v dt from t1 to t2. Or I can write that as the integral of n dot dr from r at t1 to r at t2. Let me look at this integral and see if I can get anywhere. The integral from t1 to t2 of n, which is n along En. How can I express the velocity of the particle going down this rail? Is more easily expressed in Cartesians or in some other basis?
Wouldn't it be
Surfing, and what would be the velocity of the particle?
VET.
VET. Great. Do we all agree? Right. And what is En dot ET? 0. So that's just 0. So what can you say about the normal force and its work throughout this motion?
No work.
Yes, the normal force is workless. Its work is equal to 0. Why is it workless? Because the normal force is always perpendicular to the velocity, right? The normal force is along En, the velocity is always going to be along ET. So normal force is perpendicular to the velocity. This should mean that it's also perpendicular to the displacement. So let's look at the displacement. If I look at this integral, the integral from R of T1 to R of T2, N is N En. The displacement expressed in the steady-finite basis is ds Et. ds Et. And again, En dot Et is 0. They're perpendicular. So that's also equal to 0. So the normal force is workless. And that works it for rail A and for rail B. Does that make sense? Any questions? Okay. Next, let's look at the weight force. The work of the weight from 1 to 2 is the integral of the weight dotted with V dt from T1 to T2, which is also equal to the integral from R of T1 to R of T2 of W dotted with dy. The weight is equal to minus mg Ey. So technically, evaluating either one of these integrals, I should get the same answer, right? Let me work on this one. The integral of minus mg Ey dot dr. How do I express dr? How should I express dr? In which basis should I, which basis should I choose? Cartesians, probably. The weight is already expressed in Cartesians. So that's going to be equal to dx ex plus dy ey plus dz ez. Raise your hand if you're okay, if you're with me so far. Great. Any questions? There should be questions. Questions? Okay. So what is this dot product equal to? That should be quick and easy. Not 0. Negative mg minus mg dy. Great. And that's integrating, now we're integrating from y at t1 to y at t2. And that's just equal to minus mg y at t2 minus y at t1. Right? So that would be the work of the weight from 1 to 2. Okay. A lot of observations to make here. The work of the force is usually path dependent. This definition says that the work of the force is path dependent. But for this particular weight force, the work of the weight only depended on the endpoints of the trajectory. Remember, it didn't matter if we're going through path A or path B, the work of the weight is the same. That's because the weight is a special kind of force that is a conservative force. We're going to talk about that in a bit. So for those conservative forces, their work only depends on the endpoints of the trajectory. But that's not always true. Not all forces are conservative forces, in other words. Okay? Let us see. Questions first? What would change if we had friction? So if the particle was experiencing kinetic friction as it is sliding down. So what if the rail is rough? Okay. If the rail is rough and the particle is still sliding down, what additional force do we have acting on the particle? Friction. What kind of friction? Kinetic friction, exactly. So we have now the weight, the normal force, and the friction force. And the friction force is kinetic. So is it known or unknown? Is it unknown or is it prescribed? Prescribed. What is it equal to? Yes? Minus mu k, the magnitude of the normal force, v over vira. Now, the magnitude of the normal force in this problem is just n. The velocity of the particle, v is the velocity of the particle minus the velocity of the surface underneath it, or the point underneath it. That's the velocity of the rail, which is 0. So again, that's the definition of the kinetic friction force. You remember that from last Thursday? Right? Minus mu k n, magnitude of the normal force, VRL over VRL. What is VRL? It's the relative velocity of the particle relative to the surface underneath it. So the surface underneath it is not moving, so the VRL is now just the velocity of the particle, which we have written as v et. So VRL now is equal to VET over the magnitude of VET. What is the magnitude of VET? What is the magnitude of this vector VET? That should be easy. What is the magnitude of ET? 1, right? It's a unit vector. So what's the magnitude of V times ET? Just V. Do I have to put an absolute value over V? No, because it's positive. It's defined to be always positive. So that's just VET over V, so that's just ET. So the kinetic friction force is equal to minus mu k n ET. Okay. Any questions? That's important. That's part of your quiz on Thursday. Questions? Okay. So the work of the friction force from 1 to 2, now it's equal to the integral of F dot V dt or F dot dr. The friction So if I look at form of the integral, yes.
When you calculated your v relative vector up in the corner over there, I can't quite read what those subscripts are.
So that's the velocity of the particle, and that's the velocity of the rail.
Of the what?
Rail, the rail.
Okay, gotcha.
You're welcome. So evaluating this integral now, that's the integral equal the integral of the friction force minus mu k and et. Which form of dr should I use? Do you think is more convenient? Serifrene, so that's going to be dset. So that's going to be the integral from s at t1 is n constant? Can I take it outside the integral? Like I did for the weight, for example, I took mg outside the integral. Is n constant? Can I take it outside the integral? Yes. Exactly. For the smooth, for the vertical, or for the straight rail, rail A, the normal force is going to be constant. I can take it outside and I can say minus mu k the integral of ds, and that's going to be equal to minus mu k delta s. But for B, n is not constant. The normal force is not constant. It's going to vary depending on where I am on the rail. So in general, n is a function of the rail. So n is a function of s. For A, it's constant. So n of s is just some constant. For B, it's not constant. So in general, to be able to find the work of the friction force, I'm going to need to know the shape of the path. So the work of the friction force depends on the path. So whereas the work of the weight did not depend on the path, it only depended on the endpoints, the work of the friction force depends on the path. Any questions? Is the friction force a conservative force? No. Unlike the weight, it's not. Now we're going to do a more derivation of the work energy theorem. Before we do that, let us define the kinetic energy of the particle. Yes. 1 second. What's the question?
You said that the friction force is dependent on the path, and it's the same thing for the normal force, right?
Yes.
So there are cases in which the normal force is what, not conservative?
The normal force is not conservative. So in this case, we found that the normal force is workless. Doesn't mean that it's conservative. Can anyone think of a that's actually a great question, by the way. Can anyone think of a situation where the normal force is not workless? So usually in a lot of the cases where a particle is moving on a rail, the normal force is perpendicular to the velocity, perpendicular to this displacement, and its work is zero, it's workless. But is there any case where the normal force is not perpendicular to the displacement? I can think of one problem you did in the SATs. in the balance of linear momentum sets. Not when it's weightless. We looked at that problem in class. Remember the, yeah?
Roller coaster?
Not the roller coaster. The roller coaster is like this problem where the normal force is always perpendicular to the velocity. Exactly, the elevator problem. Remember there was a woman in an elevator carrying a box? So if you look at the normal force acting on the woman, is that perpendicular to the displacement of the woman or the velocity of the woman? No. So in this case, the normal force is not workless. The same as the normal force, if you want to call it the normal force, acting by the woman on the box. That's also not workless. So if the rail is moving, if the rail itself is moving, then the normal force is not workless. Okay? So it is not always true that the normal force is workless. In general, the normal force depends on the path taken by the trajectory. The normal force is not conservative. We will learn about the conservative forces we're going to use in this class. There are only going to be 3. Any constant force, including the weight force, that's the conservative force. The spring force is conservative force, and we're going to learn about the gravitational force. Okay? Let's go back to the work energy theorem. To do that, we're going to define the kinetic energy of a particle of mass m, velocity v, as t is equal to half mv dot v. And that's just a definition. But you're going to see why we define that quantity this way in a few seconds. Well, I want you to do, what I want you to do now is to calculate the derivative of the kinetic energy. Please go ahead and do that. Take a minute, calculate the derivative of the kinetic energy. Okay, what's the answer? What's the derivative of half mv dot v? Let's take mass to be constant. What is it going to be? Ma. That's a vector. But the derivative of a scalar, should it be a vector or a scalar? The kinetic energy is a scalar, right? So its derivative needs to be a scalar. So what is it going to be? It's not 0. V is not constant. Remember, the derivative of a dot product is calculated using the product rule. Okay, so what's our answer here? I need someone from the back row to help me. What's the derivative of t? Thank you so much. What's the derivative of t? Everyone? mv dot What do you mean? mv dot v dot v, that? Do we agree? Raise your hand if you do. Only a few. Yes, right? Because you're taking half m v dot v plus half m v dot v dot. Okay? And v dot is, well, the dot product is commutative, so you can flip v and v dot, you get that. Which is m a dot v. Right? Okay. What is MA? F, right? F dot V. So far I have that d by dt, the derivative of the kinetic energy, which is T dot, is equal to F dot V. And what is F dot V?
Power.
The power. This, my friends, is the work energy theorem. Notice that it's derivable from the balance of linear momentum. So we basically used F equals ma to derive it. It's not independent from the balance of linear momentum. Have you seen this before, this form of the theorem? No, you've probably seen the integral, or maybe you've seen the integral with respect to time. T dot T1 to T2 dt is equal to the kinetic energy at T2 minus the kinetic energy at T1 is the integral on this side of the power dt. And what's the integral of the power dt with respect to time? Work, the work of the forces. Okay, that's a cute little derivation. Oops. Okay, yeah. So that's a cute little derivation again. The work, we define the kinetic energy as T is equal to half mv dot v. And what's nice about this derivation is that, or this definition, is that when I differentiate T, I'll get ma dot v, which is just the power, using the balance of linear momentum. So I get this form, T dot is equal to P, the derivative of the kinetic energy is equal to the power. That's the work energy theorem. I can integrate this to get another form of the same theorem. The change in kinetic energy is equal to the work of the forces. So the change in kinetic energy is equal to the work of the force acting on the system. The change in KE of a system is equal to the work of the forces. Let's test this theorem. Does it make sense? Let's look at projectile motion. Consider a projectile. Consider a projectile. Is the kinetic energy of a projectile increasing or decreasing? Okay, so your friend is saying the projectile's kinetic energy is increasing on the way up, decreasing on the way down. Is that true? Other way. So the kinetic energy is decreasing on the way up and increasing on the way down. Does that make sense with the work of the forces? What's the only force acting on the projectile? The weight. So I have my projectile and have the weight force acting on it. What is the work of the weight of the projectile during its motion? As the particle is going up, is the work of the weight positive or negative? Negative? Well, or positive? Think about it. You can chat with your neighbor. I'm going to take a vote in a bit. As the particle is going up, is the work of the weight positive or negative? As the particle is going up, raise your hand for positive. Raise your hand for negative. Right, it's negative. Why? Yes, yes. Another way to think about it is that if I look at the definition of the work, F dot dr, the weight is pointing down and dr is pointing up because I'm going up. So they're pointing in opposite directions. The dot product is negative. So the work of the weight is going to be negative. Hence, the kinetic energy is decreasing. So it makes sense. The theory is making sense so far. And on the way down, the kinetic energy is increasing. And what's this work of the weight? The sign of it as the particle is going down? Positive, right? Because dr is pointing down, and the weight of the weight is pointing down. Okay. Let's think about a person on a train. Or a bus. Okay, consider a person on a bus. And the bus is accelerating. So the bus was initially at rest, and then it's accelerating. What can you say about the kinetic energy of the person? Is it going to increase or is it going to decrease? The bus is initially at rest. So what's the initial kinetic energy of the person? Zero. And then the bus moves. So what's the kinetic energy of the person? Non-zero. Non-zero, right? The person is moving with the bus. Think about the person sitting on the bus or standing on the bus. So initially, the kinetic energy of the person is zero, and then it's increasing. It's non-zero. What causes that increase? According to the work energy theorem, the increase needs to come from the work of some force. So what force is causing this increase in kinetic energy? Yes, yes, it's the friction force, right? If the guy is standing, the friction force, if I look at the free body diagram of the person, weight and normal, and then we have the friction force. What's the work of the normal and the work of the weight equal to? Zero in this case, because they're both perpendicular to the displacement. The friction force is not perpendicular to the displacement. Actually, it's due to the friction force that the person gains kinetic energy. What would happen if there were no friction? Yeah, the guy would stay in place. The bus would slide underneath it, under him. Okay, and let's look at another problem, the one you did last week. A box given an initial velocity sliding up the incline, and the incline is rough. A rough inclined surface. What's going to happen to the kinetic energy of the box? It's going to decrease, right? Eventually, the box is going to come to rest. Why is the kinetic energy of the box coming or decreasing? Due to what forces? Friction. Not only friction, though, weight also. The weight also. Both of these forces have negative work. They're going to cause a depletion in the kinetic energy. Now, when the box attains its maximum height, and say it just slides down after that, is the kinetic energy of the box increasing or decreasing? Increasing, because it's sliding down. It came to rest, then it's sliding down. The kinetic energy is increasing. Why? What's causing the increase in the kinetic energy? If a box is sliding down a rough ramp, think about it. Everyone, think about it. So what's causing the increase in the kinetic energy of the box as it's sliding down the ramp? The ramp is rough. Is friction causing the increase in the kinetic energy? Is it some other force? Weight, right. It's the weight that's causing the kinetic energy to decrease. What about the friction force? What is the friction force doing? What is it? Yes, it's trying to stop the box. So the friction force is going to be kinetic. It's going to cause the kinetic energy to decrease, but the weight is stronger, has a bigger effect here, and it's causing the box to slide down the incline. Does that make sense? Any questions? Okay, let's look at these sets. Open up set 11, please. If you need a hard copy, I have some here. Let's look at problem 380. Please start working on problem 380. Feel free to chat with your neighbors, come up with a strategy to solve this problem, and start working on it. You are going to use the work energy theorem to solve this. Forces are vectors. Draw the free body diagram of the blocks. Can you draw the free body diagram of the box? So everyone, your first step is going to be to draw the free body diagram of the box. How many forces are acting on the box? Not two, three. You're going to draw the free body diagram of the box and then find the work of all the forces, of each one of them on their own. So
There's a normal.
there's a normal.
Like restricting its motion. Do we have
Yep.
to take that into account?
Yes. Yes.
I guess it changes then, or it changes depending on where you are.
Sorry, what are the other two forces? On the
Well, think about it. What are the other two forces acting? time. Okay? Make sure you know all the concepts really well. And we have to be quick. We have to be very quick. We have no time to question the direction of the normal force in the exam. That's something you should have learned in statics. Okay? Now here, we want to find the speed of the particle when it reaches point P for some force P applied on the particle. We're going to use the work energy theorem. The kinetic energy at time at time t2 when I'm at B, I'm going to call that TB when I'm at B, minus the kinetic energy when I'm at A is the work of the forces as I'm going from A to B. Okay? And what's the kinetic energy of the particle initially? Is it starting from rest? 0. So that kinetic energy is 0, and that TB I can express it as half mVb dot Vb, or the magnitude of Vb squared. That's what I want to find, right? That's equal to the work of the forces. Now, what are the forces acting on the particle? I have to draw the free body diagram and figure out all the forces acting on the particle. What are the forces acting on the particle? P, the applied force P. What else? The weight, the normal force. Forces are vectors. If I do not put the vector sign, then I'm making a major mistake and I'll get a 0 and it will not pass the class. I can write on the side, oh, the normal force is actually not along the vertical. It's along some direction that changes depending on where I am on the path. So the normal force is along En. P has a given magnitude and direction, cosine 35 degrees Ex plus sine 35 degrees Ey. And we're solving the problem twice, once for P is 25 and once for P is 40. And the weight, minus mg Ey. Any questions? Is that clear? So we have to be very careful about how we draw our free body diagram. If we do not know how to draw a free body diagram, that's a major issue. We should have not passed statics if we cannot do that. Okay, so then I'm looking at the work of F. F is all the forces. So that's the work of the normal force from A to B plus the work of the weight from A to B plus the work of the force P from A to B. Did I forget any forces? That's correct. That's like writing F equals ma, and when I write F equals ma, I look at my free body diagram and I add all the forces. Here I'm adding the work of all the forces. And then I'm going to find the work of each force individually. So what's the work of the normal force from A to B? Well, by definition, the work of a normal force is the integral of the normal force dot V dt from TA to TB. The normal force is along En. The velocity is along which direction? ET. Here we can easily write this integral in terms of the Serre-Frenet basis. What is En dot ET? What is this dot product equal to? 0. So the work of the normal force is 0. The work of the weight from A to B is the integral of RA, RB of the weight dot dr. So the integral of minus mg Ey. Here, the weight is more easily expressed in terms of Cartesians. The r I'm going to write it in terms of Cartesians. dx Ex plus dy Ey. We already explained how to obtain dr. And what is this dot product equal to? Negative mg dy. Now, if I want to figure out what I put on the boundary, I have to look at the differential. This is the differential in y. The boundary values are going to be y values, ya, yb. This integral is just minus mg yb minus ya. In this problem, what is yb minus ya? 1.6 minus mg times 1.6. So I got that the work of the weight is negative. Does that make sense? As I'm going up, the work of the weight is negative? Yes. Why? Because the weight is pointing down, the displacement is pointing up. They're opposite. The work of the weight is negative. That makes sense. Great. Then I want to find the work of the force P. So the P is P cosine 35 degrees EX plus sine 35 degrees EY. That's expressed in Cartesians. So I'm going to express dr in Cartesians, dx EX plus dy EY. Any questions so far? Okay. So that's equal to the integral of P cosine 35 degrees dx plus the integral of P sine 35 degrees dy. Good? And x goes from xa to xb. Y goes from ya to yb. Okay? Now P and P are constants, so I can write this as P cosine 35 degrees xb minus xa plus P sine 35 degrees yb minus ya. Right? Questions? What is xb minus xa? What is yb minus ya? Awesome. So I found all my terms. So the work of the normal force, that's 0. The work of the weight is minus 1.6 mg. The work of the force P is P cosine 35 degrees times 0.8 plus P sine 35 degrees times 1.6. I can replace P by its value 25 and I can solve for the magnitude of the velocity. Okay, that's it for this problem. Any questions? Questions? Okay, that's great. Yes?
Is the solution to when P is 25 actually 0?
No, I think that's a mistake. This is the answer. You should get a number. You'll get a number. Okay? Unless the number is negative, then there's no solution. Okay? Now let's talk about conservative forces. Let us see. Have you guys learned in calculus about conservative vector fields? Conservative vector fields. What makes a vector field conservative? Under what condition is a vector field conservative? Yes. 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 So for conservative vector field, the line integral depends only on the endpoints. Under what condition is a vector field conservative? Something has to do with gradients. No, not when the gradient is 0. The vector, well, when something else is 0. The curl, the curl of the vector field is 0. Right? So if a vector field can be written as the gradient of some function, then it's a conservative vector field. So from calculus, what's a gradient of a function? You've probably defined gradients as, or using coordinates. So the gradient of a function of x, y, and z is del f by del x, or f sub x ex plus f sub y ey plus f sub z ez. You also defined the gradients of the gradient of a function in polar coordinates. Did you? Did you talk about a definition of the gradient that doesn't have to do with coordinates, that's coordinate independent? Okay, so in general we can define the gradient of a function without depending on coordinates. So the differential of the function df, that would be, or define grad f as grad f, so the differential of the function is gradient of the function dotted with dr. Let us double check if it works. So if I have a function f of x, y, z, df is going to be equal to del f by del x plus del f, well, let me double check this. Del f dot dr. Oh, yeah. So del f, df is going to be del f by del x dx plus del f by del y dy plus del f by del z dz. That's going to be the differential of my function. Okay? And then dr in Cartesians is equal to dx ex plus dy ey plus dz ez. So I basically want the gradient of a function. I want this to be equal to the gradient of f dotted with dx ex plus dy ey plus dz ez. Then what should be gradient f for that to be equal to this? The gradient is a function, is a vector. So what should gradient f be for these two sides to be equal? Yes. Everyone double check this. Does that make sense? Does easy? Yes, thank you. Double check. Does that work? If I take the dot product of these two, do I get that? df? Yeah. So that's the definition of the gradient of a function in Cartesians, and you can use the same method to find the gradient of a function in any coordinate system. You can try polars. Now let's link this back to dynamics. A conservative vector field, well, a conservative force is basically a force that's derivable from a potential. So there's a function f that when I take its gradient, I'll get the force. So a conservative force is derivable from a potential. There's a certain function, a scalar function. When I take its gradient, I'll get the force. So for a certain vector field, there's a function. When I take its gradient, I'll get the vector field. Then that vector field is conservative. For a conservative force, well, the work of a force from T1 to T2 is equal to F dot dr. So that's just for any force, right? The definition of the work of a force. But if the force is conservative, then I can write the force as the gradient of some function. I'm going to call that function u. For a conservative force, I can write the force as the gradient of some function. Okay? Now in dynamics, we're using this convention of adding a minus sign here, but the mathematics is still the same. So for a conservative force, the force can be written as the gradient of some function. So if I want to find the work of a conservative force, I'll replace f by minus the gradient of the function. And then by definition of the gradient, what is the gradient dotted with dr? The differential of the function, right? So what is the minus gradient u dotted with dr? Minus d what? U, exactly. So I'll get the integral of minus du from t, now from its u1 to u2. I changed the boundaries because I changed the differential. And then the integral of the derivative, that's the fundamental theorem of calculus, that's minus u2 minus u1. Okay, so I can write for a conservative force, I can write the work of the force as a change in potential energy. So U is a potential energy. U is a potential energy function. So for a conservative force, I can write its work as a change in potential energy. Okay? And note that the work of a conservative force only depends on the endpoints. It doesn't matter what that function u is throughout the motion, it matters what it is at the endpoints. Any questions? Now in this class, we're going to learn about three forces that are conservative. In this class, we're going to learn about three forces that are conservative. The first one is going to be any constant force. Any constant force, C, and its potential energy is U is equal to minus C dot R. So you can double check that C should be equal to minus the gradient of U. Okay, let's double check. U, if C is a constant function, minus Cx Ex plus Cy Ey plus Cz Ez divided with xcx plus ey plus dez, that's equal to minus c sub x times x plus c sub y times y plus c sub z times z. I'll let you catch up. Yes.
Can you express any conservative force as that negative?
Yes. That's by definition. For a force to be conservative, it needs to be expressible as the gradient of some scalar function. So then the question is, what's the gradient of this u? And that's definition of the gradient. Del f by del x ex plus del f by del y ey plus del f plus z z. So what's the gradient of this function? Cx, cy, cz are constant because c is a constant. So what's the gradient of this? The gradient of u, is it equal to c? The gradient of this is the derivative with respect to x times ex. What's the derivative of this with respect to x? No. Cx, right? Cx times ex plus cy times ey, the derivative with respect to y plus cz times cz. The gradient of this, the gradient of u, or minus the gradient of u, is actually equal to c. So this is correct. So for any constant force c, the potential energy is equal to this, and you can find the work from u2 minus u1. Can anyone give us an example of a constant force that we've been using a lot? The weight force, yeah. For example, the weight force. Okay, so if in a certain problem the weight is, say, along EZ, weight is minus mg EZ, then the potential energy U is equal to minus the weight dotted with R, which is minus mgz. And the work of the weight from 1 to 2 is equal to minus 2 minus U1, which is minus mgz2 minus mgz1. Okay? Which is mgz1 minus z2. Does that make sense? You have to be careful with the weight. You can think of it as always being mgh1 minus h2, but you have to be careful. Sometimes someone might trick you and they might orient the axis differently. When we're solving the pendulum, for the simple pendulum, I'll point ex to be pointing down, and then the weight is not minus mgz, it's mgx plus mgx, so then you might get confused. Do not get confused. Always go back to the initial definition. Okay? I'm running out of space. My other conservative force is the spring force. Fs is equal to minus k r minus ra k epsilon r minus ra over r minus ra. Remember the spring force? We talked about it on Friday. That's a conservative force with potential energy is k epsilon squared. U is equal to half k epsilon squared. So you can doubly check that the spring force is equal to minus gradient u. I can call this u for a constant force, and I can call this u for the spring force to differentiate between the two u's. Okay, I will not verify this right now. It's a little bit longer derivation because you need to use the a cylindrical coordinate system. We're going to have to derive the expression of the gradient in the cylindrical coordinate system. But I'll send you a written document that has this derivation, so you can double check. So interesting that now you have an application, real world application for your calculus, which is awesome, right? So in the next homework, what you're gonna do is you're gonna find the energy of kind of first two homeworks, the pendulum with drag. You're gonna plot energy as a function of time, and then for the second homework, what was the second homework? Oh, the spring pendulum. You're gonna plot the energy of that as a function of time. Actually, that's very used in active research. When people are trying to solve a problem, they'll identify a quantity that's conserved, or they'll look at the energy as a function of time. If they expect the energy to be conserved, then to double check their solution, when they plot the energy of the problem, they need to see that it's conserved. So you'll be starting to do that. Now, for your problems, energy will not, well, you're gonna see when energy is conserved and when it's not gonna be. You can probably figure it out right now. For the pendulum, for the projectile with drag, is the energy gonna be conserved? No, why not? So the weight is conservative, but the drag force is not conservative. And for the energy of a system to be conserved, we're gonna see all the forces doing work need to be conservative. We'll talk about this. I'm jumping a bit ahead. Okay, and the other force that's conservative is the gravitational force. So let me talk about that force actually over there. So the gravitational force. So this force is due to Newton. You've probably heard of this before. If you have two particles of mass m1 and m2, the particle, for example, 2 is going to exert a force on 1 and 1 is going to exert a force on 2. For example, the force from particle 1 on particle 2, force from 1 on 2. So the force on 2 is going to be directed towards 1, F1 on 2. M1 is going to pull, or it's going to attract M2 towards it. Is going to be proportional to the gravitational constant, the masses of the two, over the, and inversely proportional to the distance squared. Yes. So if M1 is greater, the push is going to be greater. If M2 is bigger, the push is going to be bigger. G is called the gravitational constant. You can find that in tables. You have that value in the table in set 11. Yes?
Is there a difference between like the notation work where you have like F comma 1, 2, and in this case where you have F sub 1 over 2, or is it like?
Yes. That other work is the work from state 1 to state 2 and from T1 to T2. Here it's from the work from M1 on M2. So there is the work from time T2 to time T1, or T1 to T2. That's the force from M1 on M2. Okay? And that force is going to be inversely proportional to the distance between them. And then it points along R1 minus R2. So that's just a unit vector, R1 minus R2. Yeah, that's R1 minus R2. Pointing from 2 to Okay, so this vector field is conservative, and its potential energy, call it UG, is equal to, here it's given in your problem sets, it's equal to minus G M1 M2 over R2 with respect to 1. I think I forgot the square here. Okay. Questions? Let's do an interesting little exercise. If I have some object, and I'm looking at the gravitational attraction between the object and the Earth. So this is Earth, and this is my object. So the Earth has mass sub e, that's m Earth, and I have the distance between them is the radius of the Earth plus some height above the Earth. So I want to find the force that the Earth applies on this object of mass m. Force that Earth applies on object of mass m. Okay, and I'm just going to apply the formula. Okay, the formula says that the force applied by the Earth on the object is equal to minus G, mass of the Earth, mass of the object, over the distance between them squared. So that's going to be R Earth plus H squared, and it's going to point towards the Earth. I'm going to put a unit vector U. Okay, can anyone guess what this value will be if H is small? So if H is small, meaning that the object is very close to Earth, it's small compared to the radius of the Earth, so I can take it out, I can cancel it kind of. What's the value of G me over the radius of the Earth squared? So G times the mass of the Earth over the radius of the Earth squared in SI. What do you think it's going to be? Yeah, 9.81. That's the small value of G we use. Nice, huh? Okay, so the gravity, the force of gravity we use around Earth that we assume is constant is just an approximation of this, where H is taken to be small. So it's small compared to the radius of the Earth, so we can neglect it from this calculation, kind of. Okay? Questions? Okay. So going back to conservative forces. How many conservative forces, how many types of conservative forces you should know in this class? 3. Any constant force, that includes the weight force, the spring force, and this gravitational force. Okay, one more thing about constant forces. Let's look at the work energy theorem again. T2 minus T1, the work energy theorem, is equal to the work of the forces from T1 to T2. Let me divide the forces. I'm going to divide them into conservative forces and non-conservative forces. And non-conservative forces. Okay, so I'll divide the work of the forces as the work of the conservative forces. With me so far? Now, how can I write the work of the conservative forces? The work of the conservative forces as a change in potential energy, right? So that's equal to minus U2 minus U1. plus the work of the non-conservative forces. Okay, I'll do some rearranging now. I'll get T2 plus U2 minus T1 plus U1 is equal to the work of the non-conservative forces between T1 and T2. And I'll call this T plus U, I'm going to call it E. So E is the total mechanical energy. So the change in the total energy of a system is equal to the work of the non-conservative forces. Wow. So the change in the total energy of the system is equal to the work of the non-conservative forces. First, any questions on how I got here? Any questions? Okay. So then the question to you is, when is the energy of a system conserved? For E to be constant throughout the motion of the system, when is the energy, that means that the energy of a system is conserved. When is that true? When is E constant? When is E conserved? When is it going to not change? E1 is going to be equal to E2 always. Under what condition do I get that? The work of the non-conservative force, this term should be what? 0. So the work of the non-conservative forces should be 0. If the work of the non-conservative forces is 0, then the energy, if work of non-conservative forces is 0, then the energy of a system is conserved. If the work of the non-conservative force is 0, then the energy of a system is conserved. So for example, again, for a projectile without drag, is the energy of the projectile conserved? Projectile without drag. Yes, because what's the only force acting on the system? It's weight, and weight is conservative. So that is 0. We have no non-conservative forces. So this is 0, energy of the system is conserved. For a projectile with drag, is the energy of the system conserved? No, why not? Because we have drag, it's a non-conservative force and it's not workless. For the problem that we just did, the 380 in this set, the particle going down the smooth rail or going up the smooth rail, is the energy of that particle conserved? Yes or no? Think about it, discuss. Okay, so for the rail problem, is the energy conserved? Raise your hand for yes. Raise your hand for no. For the no, can you say why energy is not conserved? So we need to go step by step. What are the forces acting on the particle that's on the rail? Okay. Okay. Before you start with your quiz, that's very important, so be careful. Before you start with your quiz, For the particle that's under it, the forces acting on it were force P, the weight, and the normal, right? Right? The weight is conservative. Force P, is it conservative? Yes, why? It's constant, it's conservative. So I don't need to look at these forces. Force N, is it conservative? The normal force? No, it's not conservative. But what is its work? 0. So it's workless. So is the energy of the system conserved? Yes. Why? Because all the non-conservative forces are workless. So the work of all the non-conservative forces is 0. So the energy of the system is conserved. Okay? Wait. So please work on this quiz. You can work with up to groups of 3. And I'll give you answer sheets. Please answer on the answer sheets. We'll only take the answer sheets this time. Make sure to be very clean and tidy. If you need scratch paper, use scratch paper. But we need you to be clean and tidy now and in the midterm especially. You have to work from top to bottom. Do not scratch things out. If you scratch things out, use scratch paper. Yeah, just be very tidy. Yeah, you'll submit one paper per group. You'll submit one paper per group. So you can work individually, in pairs, or in groups of 3, submitting one paper per group. This is the answer sheet.
Okay.
This is extra. Here you go. You can use the extra papers as scratch. One answer sheet, that's the answer sheet. That's the answer sheet, sir.
Oh.
You can use the rest as scratch.
Wait, so should we each turn in our own answer sheet? Or
No, one answer sheet per group. One answer sheet per group. Yes. What can you get for you? Here you go. You're welcome. Everyone has their sheet? Right. Being organized is very important.